Inside, it was a very difficult thing to do, very stressful for a lot of people. But at the same time, if you step back and look at it now from today's perspective, in terms of the dollars that we saved and that we're freed up to invest in other science activities, I think it was a very wise choice.
So in late '88, the Congress decided that they would approve the first lump of funding for Chandra, and they directed us to show that we could actually build an X-ray telescope which focused to the level of an arcsecond of angular resolution. And there was a lot of skepticism as to whether you could actually build a mirror that good. They gave us a set amount of money in 3 years to build and test this X-ray mirror. So we had to start with the glass and then the machinery to polish it and measure it, and a test facility at Marshall Space Flight Center, the X-ray calibration facility, to actually test the X-ray performance of the mirror.
So there was an insistence that we prove that we could build the telescopes that we thought we could build, and that was a major achievement. And to have a senior congressional staffer flying down to Marshall Space Flight Center to witness the test of a scientific instrument, that's not your typical situation. So that got a lot of scrutiny. By the way, because that was successful, he became a convert, and so he was one of the people in the government who helped make it happen.
After the earlier successful testing at Marshall of the initial outer pair of mirrors and the redesign of the observatory that resulted in the change of orbit, the completed mirror assembly arrived in Huntsville for testing at the X-ray calibration facility.
So that part of the analysis of the whole process of getting Chandra into orbit and understanding how it works involved a lot of late nights. There was a 24-hour operation at Marshall, a lot of analysis, a lot of seat-of-the-pants work where you had to take results that have just come in from a detector, go back to your computer, try and analyze them, understand them, what was happening, and then redesign a test the next day in order to verify whether what you think you saw was actually correct.
On August 19, 1999, after years of engineering, tests, and a successful launch,
look at that picture. Isn't that amazing?
The Chandra team members gathered in the new control center at Cambridge. There was obvious and understandable excitement as the initial or first light image of Cassiopeia A emerged.
I was in the room when the scientists were all jumping up and down, waving their arms. I was saying, Chandra's open for business.
We got spoiled with this observatory because it operates itself. The spacecraft operates so well and so smoothly and so efficiently that we don't have a lot of problems. We don't go into safe mode every few days, every few hours, every few months. In fact, we were wondering early in the mission whether perhaps we would ever go into safe mode because the observatory is operating so well.
The reason for the observatory's smooth operation is a dedicated team of professionals that ensure that Chandra continues to exceed expectations, day in, day out.
And we have, I've termed it, the term I have for how we run things around here is it's conservatism, but it allows for innovation. So we have this philosophy of being very conservative with what we do, but we don't stifle innovation. We allow people to innovate. If they come up with a better and brighter idea, we'll go ahead and look at it and put it in place if it makes sense.
We communicate to the spacecraft through the Deep Space Network. And so this control center here, when we have a real-time contact with Chandra, is connected to one of the Deep Space Network antennas. We have 3 passes per day of 1 or 2 hours each. And our basic operations concept is that once a year there's a call for proposals from the science community, international science community, as well as here in the US.
And that culminates in June with more than 100 astronomers coming from all over the world to read. We get about 800 proposals per year. So we sit them in 12 panel rooms and they discuss all these proposals and decide which ones get the time, which ones are the best or the most exciting or the most possible.
Once we have those targets, our mission planning teams, both the science teams, mission planning team and the flight mission planning team, can develop long-term and then short-term schedules. And so on a weekly basis, a detailed schedule is developed and a set of command loads that fold in all of the engineering constraints. Can't point too near the sun, can't point too near the bright Earth, and so on. And these get converted to command loads. And those command loads are uplinked About once there's a 1 week schedule which gets uplinked about every couple of days. It's broken up into sections. Once it's uplinked to Chandra, Chandra operates autonomously in its orbit.
Not only does Chandra operate largely autonomously, it does so with astounding robustness.
So I think it's a testimony to the people who designed and built it, and of course it's a testimony a little bit to good fortune as well, because there are, on almost any space mission, there are random failures. They can sometimes be something small that you have a redundant way of dealing with whatever it is that's failed or it's not essential for the ongoing performance of the observatory. And we've had a couple of small things on Chandra, but nothing which has affected the primary performance. The Chandra project was very challenging, and it had, I guess, unfortunately, it had a long history from the time we first thought about it until we started actually building things. And that period of time gave us some opportunity to go through some of the challenges together. And I think we realized that everybody brought some unique expertise to the table. The world's expert on X-ray telescopes was Leon van Spaebroek, who competed and was chosen to be the telescope scientist. He's unfortunately passed away, but he was with us for the first few years after Chandra launched, and he got to see the beautiful images that Chandra returned.
In addition to Leon van Spaebroek, many people contributed to the future telescope's success. Bruno Rossi, of course, and the invaluable leadership and vision of Nobel Prize winner Riccardo Giacconi.
Giacconi is an extraordinary leader, a scientific leader in particular, because he's an excellent scientist. He has the highest integrity and sense of what's important, and he inspires people.
He had enormous vision of where the field of X-ray astronomy was going to go and what was going to be useful.
What he didn't see, of course, were the answers, but he saw the questions. He saw that X-ray astronomy was going to be important. He saw that technically you needed X-ray telescopes. He saw that some of the most important questions were, how do galaxies evolve? How do clusters of galaxies evolve? And he saw the ways how you would go about answering those questions. The program was originally called the Advanced X-ray Astrophysics Facility, what a mouthful, or AXAF for short, which is sort of sounded pretty harsh. It was a facility so that it wouldn't be a telescope, because we were asking for something new, and we had already asked for the Hubble Space Telescope, so we didn't want to ask Congress for 2 telescopes. We were going to ask for a facility. And this was the name for many years. And then as we approached the launch, we held a contest. We ultimately chose the winner, the name Chandra, which was short for the last name of Nobel Prize-winning Indian-American astrophysicist Subramanian Chandrasekhar. And it was a very appropriate choice of name because he did a lot of work on astronomy and astrophysics, hence the current name Chandra. Very fitting.
With a superbly built observatory up and running and properly named, attention turned to the detection of X-rays. But what are the main processes which generate X-rays?
There are a number of different ways that X-rays are generated in the universe, and one of those ways is temperatures very high. To produce X-rays, you need a lot of energy, therefore you need a lot of heat, and we're talking about temperatures of millions of degrees. The hot skins of stars are like that. Another way is having charged particles move in magnetic fields. Very strong magnetic fields or very energetic charged particles, or both. And we have that situation, for example, in the vicinity of these compact objects called neutron stars, where we have huge magnetic fields. Those are 2 very principal mechanisms. Another way of adding energy, probably about the 3rd category, is gravity. Accelerate a charged particle really hard, and it will radiate X-rays. And if you just let it fall to the surface of a very compact object, neutron star, or in the vicinity of a black hole outside the event horizon so you still can see the X-rays, that's a way of producing X-rays.
The very first images began to give you a sense that Chandra was going to be very different. The official first light image of Cassiopeia A, in just about an hour and a half's exposure, we could see a faint dot in the center of the image, which is the neutron star that was formed when that star blew up 300 years ago.
We've seen this so clearly, how beautiful the Chandra images are, They're not only beautiful, they're spectacularly scientifically informative. One just has to look at, for